Hello. In the previous video, we talked about the cramers rule and we proved a theorem such that if you have a system of equations ax is equal to b, then x is equal to a inverse b, and we can find x1 is equal to determinant of a1 over determinant of a, and x2 is equal to determinant of a2 over determinant of a, and similarly x3 is equal to determinant of a3 over determinant of a. Okay, and if you have other variables also, you can find the in the similar pattern. Okay, so let's do an example based on this Cramer's system, Cramer's rule. So here is an example. You have given a system of linear equations. You are given three equations and you have to solve it by using Cramer's rule. So first of all, I will check what is my A. So my matrix A is the coefficient matrix. Here the coefficient of Ax is 1, so I will write 1. The coefficient of y is 3, so I will write 3. In this equation, there is no coefficient of z, so that means z is absent. So I will consider the coefficient of z is 0. And come to this equation, the coefficient of x is minus 1, so I will write minus 1 here. And the coefficient of y is m. Coefficient of z is minus 1. Then we will move towards the last equation in which the coefficient of x is m, the coefficient of y is 1, the coefficient of z is m. So this is your matrix A. And what is B? B is just these elements 1, 0, minus 2. So I will write 1, 0, minus 2. And if we talk about the variable matrix, which is x, since your x is consisting of x, y, z, sometimes it is x1, x2, x3, but here we have x, y, z, doesn't matter, x, y, and z. Since the Cramer's rule says you have to find the determinant of A every time, but you have to find the determinant of A1, A2, and A3 also. Okay, first of all, we will find the determinant of A. So, determinant of A is, you can either write determinant of A or you can write this way. Both are the same. So here you have matrix A and we have found its determinant. We have to find its determinant actually. Okay. In order to find the determinant, we will check which row or which column has most number of zeros. So you will check the first row has more number of zeros. So it is better if we make this element 0 also by using column operations. So in the similar way, we will use the column operation just we have done in the previous couple of videos for the rows. So I have to make here 0 and I will use this 1. What can I do to make here 0? How can I make here 0? So this element is 3. So what can I subtract? I have to use this, right? This 1 is used here, right? So what number should be here to make it 0? So the obvious answer is 3, okay? So this 3 belongs to column 2 minus this 3 is the constant and this 1 belongs to column 1, okay? So I will write C2 minus 3C1, okay? Because this corresponds to column 1. So this is the operation which I'll perform. So I will make changes in this column. So these two columns will remain the same, 1 minus 1 m, 1 minus 1 m. And this column, in this column we will make changes. These changes I will make in this column. So it is C2 minus 3 times C1. So first of all, I will write C2 as it is 3M1, 3M1. So this is C2 minus 3C1. So I will write minus 3 everywhere. And then C1. What is C1? C1 is 1 minus 1M. So I will write 1 minus 1M. Okay. And the last column as it is 0 minus 1M. Okay, if I simplify these values, 1 minus 1M, this becomes 0, and this is also 0. M plus 3, I will write M plus 3 here. And this is 1 minus 3M. 1 minus 3M. And the last column is 0 minus 1M. Okay, now I can expand this determinant along the first row. How can I expand? First of all, I will write minus 1 to the power 1 plus 1 times this element 1 times the determinant obtained by deleting this row and this column. I will have M plus 3 minus 1, 1 minus 3M and M, plus minus 1 to the power 1 plus 2. This number is 0, so 0 times any matrix is 0, plus minus 1 to the power 1 plus 3 times this number. Since this number is 0, so I will write here 0. 0 times any matrix is 0, so I am not going to write these matrices. So this entry is 0, this entry is 0, whatever they are, I will left with only this entry. So this entry is M plus 3 times, so this is 1, M plus 3 times M, M plus 3 times M, minus the product of these two, 1 minus 3M times minus 1. If I simplify these values, I will have M square plus 3M. This minus will multiply here, it will become plus 1 minus 3M. Okay, so M square plus 3M plus 1 minus 3M. 3M minus 3M will get cancelled. You will get M square plus 1. So this is the determinant of A. So the determinant of A is M square plus 1 here in this case. And from the theory of the Cramer's rule or the Cramer's system, we know that the Cramer's rule can only work, or the system of equation has only unique solution if the determinant of A is not equal to 0. And we don't know that this term is 0 or not equal to 0. Okay, so what will happen if M square plus 1 becomes 0? Then M square will be minus 1. So in the real numbers, M square cannot be a negative number, because the real numbers are the numbers whose square is always positive. The square of any real number cannot be negative. If we get a number whose square is negative, that is not the real, that is called imaginary or complex number. So this cannot happen as long as we are in the real line. So this guarantees that the determinant cannot be 0 as long as we are in the real system. So we are okay with that. The determinant is not equal to 0, so the Cramer's system will work. In other words, the system has unique solution. We can use the Cramer's rule. Okay, so using the Cramer's rule, we have x is equal to the determinant of A1 over determinant of A. Okay, and similarly, y is equal to the determinant of a2 by using Cramer's rule over determinant of a, and z is equal to determinant of a3 over determinant of a. We already know what is a determinant of a, but we don't know what is determinant of a1, what is determinant of a2, what is determinant of a3. Okay, so let's first find x. X is equal to determinant of a1 over determinant of a. Put the values. Determinant of a we have just found, which is m squared plus 1. What is a1? a1 is obtained by replacing the first column by the matrix B. Okay, I mean, in the first column, if you replace B, you will get a1. Make sense? So what I have done, I have written matrix A, but its first column I have changed, I have replaced by B. You can check. My B was 1, 0, minus 2. If I write this thing here and the other things, I mean these two columns as it is, we will get this matrix, okay? Now I have to find this determinant in the top, on the top. So in order to find this determinant, it's easy to make here 0 first, because if I either you can make here 0 or you can make here 0, it's up to you. Okay, so if I make here 0, what can I do? How can I make here 0? I mean, it's minus 2 plus what number times this pivot entry? Of course, 2 times 1, okay, because minus 2 plus 2 will get 0. And minus 2 corresponds to R3, plus 2 is the constant, and 1 corresponds to R1. So I will perform this operation, R3 plus 2R1. I will write here R3 plus 2R1. This operation I will perform here. Okay. So minus 2 plus 2 times R1. Okay. Minus 2 plus 2 times R1. 1 plus 2 times 3. Okay. 1 plus 2 times 3. And then m plus 2 times 0. I will write m plus 2 times 0 is 0. Okay, so I will write just 0 here. Doesn't matter. And these two rows will remain the same. 0, m minus 1, 1, 3, 0. Okay, and in the denominator we have m squared plus 1 as usual. If I solve it, I have 1, 3, 0. 0 m minus 1 and 0, this is 7 m, and here I have m squared plus 1. Now if I expand this determinant along the first column, so first of all I will write this number times its cofactor, and then I will write plus this number times cofactor plus this number times cofactor. So I will write only this number times cofactor because these two numbers are 0. Okay, so m squared plus 1. So I will write 1 times its cofactor, means this whole thing. M minus 1, 7 times m. So this is the determinant. So the determinant gets reduced by making here zeros. Okay. Now I can find this determinant easily by multiplying these two minus the product of these two. Okay. So I have the product of these two is m squared minus the product of these two is plus 7. Okay, because minus 7 is plus 7 over m squared plus 1. So this is your x. Similarly, we can find y. So y is a2, the determinant of a2 over determinant of a. And the determinant of a2 is obtained by replacing the second column by b, and the other two columns will remain the same. Okay? So I have written down a2 by replacing this by b, and the other two columns remains the same as they are in a. Now we have to expand this determinant. We can expand this determinant as usual, but if it is easy if we make here 0 in any column. I can make the here 1 and here 0, here 2 zeros, but here I have to make 0 at 2 places, but here I have to make 0 at only one place, so I will make here 0. Okay, look, how can we make here 0? Again, this is minus 2 plus some number times the pivot entry is 1. So here the scalar is obviously 2. So this means it is R3 plus 2 times this number is coming from R1. So this is the operation which I'll perform, R3 plus 2R1. So I'll write R3 plus 2R1. M squared plus 1. Okay, so I will write R3 plus 2R1. So first of all, I will write R3 plus 2R1, 2 times 1, and then this plus 2 times R1, minus this plus 2 times R1 is 1, okay? Then this number is M plus 2 times R1, 2 times 0 is 0. So, and the rest of the two rows will remains the same, minus 1, 0, minus 1, 1, 1, and 0, okay? If I simplify these values, I'll get 1 minus 1, M plus, and then 1, 0, 0, and then 0 minus 1, M. 0 minus 1, M. Here, as usual, M squared plus 1. So I will write M squared plus 1. Just like previously, I have told you that the determinant can be expanded by any row or by any column. So I can expand this determinant by this column. If I expand this determinant by this column, so first of all, I will write this element times its cofactor. But this element is, so I will write minus 1 to the power, this element is in the first row and second column. So I will write 1 plus 2 times this element is 1. So I will write 1 times the submatrix obtained by deleting this column and this row. I will get minus 1 M plus 2 minus 1 M. Okay, and then it's the turn of this and the turn of this, because these two are zeros, so I will not write plus zeros, okay, because 0 times all of the other entries are 0. So M squared plus 1 here I will get. If I solve it, this is minus 1, because minus 1 to the power 3, which is an odd number, so minus 1 to the power odd number is minus 1. So I will have minus, so this thing is minus 1 times this determinant. This determinant is minus 1 times M, which is minus 1, minus M. Minus 1 times M is minus M. And minus 1 times M plus 2. I will write minus 1 times M plus 2. Okay? Over M squared plus 1. This minus as it is, minus M, minus, multiply this minus inside. Okay, multiply this minus inside, it will become plus. Okay, m plus 2, and I will write then this m plus 2 over m square plus 1. This m and minus m will get cancelled, so I will have minus 2 over m square plus 1. Okay, so this is the value of y. Now we have to find the value of z, which is the determinant of a3 over determinant of a. Since the determinant of a3 is obtained by replacing a third column by b in the matrix A. So this is the matrix A. If I replace the third column by matrix B, then I will get A3. So I have written Z is equal to determinant of A3 over determinant of A. Okay, again, I can check. This is the column in which the last element is non-zero, but this is 0. So I will make here 0 also to expand the determinant. Still, how can I make 0 here? I will write minus 2 plus 2 times 1, which is R3 plus 2 times R1. So still I will perform the same operation. So I will write R3 plus 2 times R1. Okay, so first of all, I will write the last row where we have to make changes. I will write m plus 2 times 1, and then 1 plus 2 times 3, and then minus 2 plus 2 times 1. And the rest of the 2 rows remains the same. If I simplify this thing, I will get this matrix, this determinant. Now I have to expand the determinant along this column. If I expand this determinant along this column, so first of all, I will write this element times its cofactor. So I will write first of all minus 1 to the power 1 plus 3, because this element is in the third row, in the first row and third column. So that's why I write minus 1 to the power 1 plus 3 times this element 1 times the submatrix obtained by deleting this and deleting this, minus 1m, m plus 2, 7, plus, what will I do now? Then the turn of this, but these two elements are 0, so 0. So no need to write zeros here, okay? And in the denominator, I have m square plus 1 as usual. This thing is plus 1 because minus 1 to the power 1 plus 3 is 4, which is even number. So that's why it is plus 1. So plus 1 is not necessary if you don't write. So I have only this determinant. Minus 1 times 7 is minus 7, minus the product of these two is m times m plus 2 over m square plus 1. If I simplify this thing, minus 1 minus m square minus 2m over m square plus 1, it is equal to minus, because every term is minus, so I can take minus common. So this is equal to m square plus 2m plus 7. Why I am writing plus everywhere? Because minus is common among all of these terms, and I have written here because this means it is common in all of these terms. So that's why here I have written plus everywhere, because I took minus common. So this is z. Okay, so I have found x, y, and z. So that means if I write the solution, my solution is x, y, z equal to, first of all, I will write the value of x. The value of x was m squared plus 7 over m squared plus 1. The value of y, which we have found here, it is minus 2 over m squared plus 1. And the value of z, which we have found here, it is negative. Okay, you can write negative m squared plus 2m plus 7 over m squared plus 1. You have two ways to write. Either you can write negative here, or you can write negative here everywhere. And don't write here. It's up to you, whatever you want to write. So this is the solution of this system. So this is the simple way to find the solution of any kind of m by m matrix using Cramer's rule if the determinant is not 0.